Hello, my name is Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 11 in my Computer Networks lecture series, where we evaluate the performance of stop and wait ARQ. Now, I guess the first logical question is, what do we mean by performance? Well, we've mentioned a few times that the benefit of frame retransmission is we give the illusion of an error-free link over a physical layer that is subject to bit errors, because as long as our error detection scheme is good, we can check every frame that comes in. If there's any bad bits in that frame, we can just ask for a retransmission and just keep asking for a retransmission until the frame comes through okay. So as far as the upper layers of the protocol stack are concerned, we never ever give the upper layers a frame that has any bad bits in it. And so we take an error-prone link and make it appear like it's error-free. However, of course, there is a cost to this, and the cost is the time it takes to do these retransmissions. So anytime we have to retransmit a frame that's already been sent, we're taking up time, or we're stealing time away from transmitting new bits for the user. And also, we have to add some overhead to the frames, our checksum, our header. The acknowledgement frames take up a little bit of time in the channel as well. So there's also this overhead that takes up or steals away some of the raw throughput from our physical layer. So basically, when we talk about evaluating ARQ performance, we're talking about calculating the effective throughput experienced by the user once we account for all of this quote-unquote wasted time spent retransmitting frames or sending ARQ frames or sending, overhead headers and checksums and stuff like that. And so this is actually going to be the first point in this lecture series where we calculate an effective throughput. And you're going to see that we do this over and over and over again. So the fundamental trade-off of all protocols is that they give us a certain desired performance, but there's also a cost. And because throughput and bitrate is such an important parameter for network designers, we typically sort of our go-to performance calculation is always effective throughput. Given once we add in all this functionality and this overhead and retransmissions and whatever else, what is the effective user experience in terms of the data rate that the people who subscribe to our network might enjoy? So in order for us to calculate effective throughput or even define it, we're going to have to introduce a bunch of notation. And so there's a lot going on this slide. There's a diagram and a whole bunch of variables. And I'm gonna just kind of step through everything we've got here to explain everything. And what I would recommend is, for you to take a screenshot or print a copy of this particular slide and sort of have it kind of sitting beside you for kind of our subsequent discussion once we get into the derivation, because I'm going to be using all of these variables and it's kind of nice to have them laid out in a place that you can refer to them. So to start out with, at the top of the slide, we've got our sort of now familiar packet exchange timeline type diagram. Node A is our transmitter, node B is our receiver, but we've added a little bit more detail to this diagram than we used in our previous modules. So first of all, we've explicitly written out the sort of the start of a frame transmission and the end of a frame transmission. And so this arrow indicates the start of the frame, so basically the first bit that originates from node A and then arrives at node B, and the time it takes for that first bit to arrive at the receiver is equal to the propagation time. And propagation time is defined down here. And it's the delay required for a bit to travel along the path between the transmitter and the receiver. And so basically this is, when this is a direct transmission, this is essentially the speed of light, more or less. You know, the propagation of a voltage signal along a wire is typically a little bit less than the speed of light, but it's pretty close. So obviously this is very fast. But it's not as fast as you might think in terms of kind of modern network timescales. So it takes, for example, a microsecond for light to travel 300 meters. And that seems pretty fast, but in a gigabit per second network, the duration of a single bit is only a nanosecond. So now that we're working with gigabit type networks, the speed of light becomes something that we can no longer ignore. And we're going to kind of come back to this point because I think it's kind of a cool aspect of network design. Like, networks have gotten so fast that the speed of light is actually a big deal. And we're going to see later on when we talk about MAC protocols that, you know, the slowness of light is something that causes us issues in some of our networks. So anyways, we explicitly show the first bit in our frame, and the last bit in our frame is shown by this second arrow. And the time between the first and the last bit we denote as T frame. And T frame is just the time required to transmit a frame over our physical layer. And it's equal to the total number of bits in our frame divided by the raw throughput of our physical layer. And the total number of bits, NF, is equal to the number of data bits in the information frame plus the number of overhead bits in the information frame. And this is a typo. This should be information frame there. And, you know, again, it takes a certain amount of time to send the data frame. So that's why we make a note of it here. And again, in the previous modules, we showed a whole frame. We represented the transmission of an entire frame just by one arrow, but for the purposes of this discussion, we have two, for the first bit and the last bit. So once the final bit arrives at our receiver, we take a certain amount of time to process that received frame. And this processing time, defined down here, is the time it takes to perform the error detection primarily, determine whether or not there's a bad bit in the frame, and then figure out whether or not we should send an acknowledgement back for that frame. Or yeah, whether or not we should send an acknowledgement back for the frame. And so once we're finished with that processing, we send our acknowledgement back, and our acknowledgement is represented by two arrows. It goes from the receiver back to the transmitter. This arrow is the first bit in the acknowledgement frame. This arrow is the last bit in the acknowledgement frame. The time it takes, or the time between the transmission of the first and last bit in the acknowledgement frame, is TAC, which is equal to the number of bits in the acknowledgement frame divided by the raw data rate of the physical layer. And once we receive the acknowledgement back, we have a certain amount of processing time, and this is the amount of processing time that it takes for the transmitter to sort of receive the information or receive the acknowledgement frame, process it, think about it, and decide what to do next. And so the total amount of time it takes to do a single exchange in stop and wait ARQ is denoted by capital T. And capital T is basically from the point where we send the very first frame, or sorry, the very first bit in our information frame, to the point where we have finished receiving the acknowledgement for that frame and processing it. And we make a couple of assumptions here. One is that the processing time for the receiver and the processing time for the transmitter is equal. It's not going to always be exactly equal, but we make that approximation to simplify things. And so, you know, again, just a couple of last notes. Oops. This should still be I. We've gone through all of these variables. R, again, is the raw data rate of the physical layer. So in our bit pipe model, if you remember, we defined the physical layer as a bit pipe, and it had a certain probability of error and a certain raw physical layer throughput. So that's the R that we're referring to here. And what I'm going to do now is we're going to take this picture and these variables, and we're going to derive the effective throughput of the stop and wait ARQ system in an error-free situation, and then when errors occur. And as I said, you know, keep a copy of this page sort of set off to the side, because I'm gonna kind of going forward assume that you understand what all these variables mean, and I'm gonna use them in the derivation. So we're gonna start our derivation by defining the total time to send one frame. And on the previous diagram, we defined this total time as capital T, and it was equal to, if you look back at that diagram, we had 2 propagation times, we had 2 processing times, we had the time it takes to send a single frame, and the time it takes to send an acknowledgement. And the time it takes to send a single frame is equal to the total number of bits in the frame divided by physical layer throughput. The time required to send an acknowledgement is equal to the total number of bits in the acknowledgement frame divided by physical layer throughput. Now, the next parameter I want to define is effective data rate. This is a very important parameter, and as I suggested at the start of the module, we're going to calculate effective throughput or effective data rate several times in this lecture series. And when we define effective throughput, we're really trying to quantify user experience, or the throughput enjoyed by the user. And so the definition for effective throughput is very logical, and it's just equal to the number of user bits divided by the time to send those bits. So it's just the number of bits that we're sending that are important to the user, so not overhead bits, but actual sort of payload bits, divided by however long it takes us to send those bits, right? So we get something in bits per second. And so as far as this stop and wait ARQ protocol is concerned, the number of user bits is equal to the total number of bits in our information frame minus however many bits we have for overhead, header, CRC, stuff like that. And the time it takes to send those bits is equal to capital T, which is this, collection of all of these terms. So it's not just the time it takes to transmit the information frame, it's the time it takes for the acknowledgement, it's the propagation delay, it's the processing delay. So we want to include everything in this term. The next term I want to define is efficiency. And efficiency is basically defined as the percentage of the raw physical layer throughput that is taken up by sending user data, or bits that are important to the user. And so it's basically the effective throughput divided by the raw physical layer throughput. So if efficiency is equal to 1, that's the highest value we can have, and that means that every single bit transferred by the physical layer is something that is meaningful and important to the user, and there's no gaps, no overhead bits, nothing like that. Obviously, we'll never ever have an efficiency of 1, but as we're going to see, we can in some cases get pretty close to 1. And this is just then equal to our expression for effective throughput, which is NF minus N overhead divided by T divided by the raw physical layer throughput. And what I'm going to do now is I'm going to take this expression, I'm going to plug it into there, and I'm going to do some algebra and some canceling of terms, and we're going to get the expression I'm going to write down on the next slide. And so if I work through that algebra, and this is something that you can do at home if you want to sort of satisfy yourself how I ended up with this expression. If you work through this algebra, you get this kind of final expression for the efficiency of stop and wait ARQ. And I am a really big fan of this expression. And one of the things I find interesting about teaching undergrad is sort of discussing the relationship of engineering to mathematics. And there are, many undergrad students out there that, they sort of, whenever we dive into a huge amount of detail, it tends to turn the students off when we dive into a huge amount of mathematical detail. And they're like, oh, this is too abstract, it's not practical, why do we need to learn all these equations? And, there's this attitude out there maybe sometimes that people think, well, this math that we're teaching in school is just sort of to kind of filter students out, and it's not really that important once you get into the quote-unquote real world. But, I would make, at this point, a really passionate argument for the value of mathematics. The value of mathematics and the value of an equation is to paint a picture about how a system behaves. And it's a picture that you get it's not a picture that you can get by just sort of playing around with equipment or even doing like sort of a computer simulation and looking at curves. The beautiful thing about a mathematical equation, or some mathematical equations, is that it very quickly paints a picture of what is and is not important for your system. And this equation is a great example of this. So we want an efficiency as close as possible to 1. And anything that makes our efficiency less than 1, we don't want. Okay, so let's start out by taking a look at the numerator of our expression. Here we have 1 on our numerator, and we have a term that is making our numerator smaller. And so ideally, we would want this second term to be as small as possible. And so if we take a look at this second term, it's equal to the number of overhead bits divided by the total number of bits in our frame. And if we want this term to be as small as possible, basically what this is telling us is that we want to have as few overhead bits as possible relative to the total length of our frame. And this makes intuitive sense, right? Like we want to send big long frames with big payloads and as little overhead as possible. And if we do that, we make the numerator of our equation as big as possible. Whoops, got overzealous with my erasing. If we take a look now at our denominator, we want our denominator to be as small as possible. And so again, we have a 1. And then these two terms serve to make our denominator bigger, right? So the second and third terms in our denominator are basically bad, and we want to make them as small as possible. And so let's take a look at what they mean. Well, the first term is equal to the number of acknowledgement bits divided by the total number of bits in the information frame. And so to make this term as small as possible, we basically want to have big, long information frames, and we want the acknowledgement frames to be as short as they possibly can be. Again, intuitively, this makes sense because, you know, we don't want to take up a whole bunch of airtime transmitting an acknowledgement frame because that's not valuable data from a user perspective. The second term basically represents the amount of sort of equivalent bits that we waste due to the propagation delay through the channel and the time we spent processing the received information and acknowledgement frames. So if we take 2 times our propagation and processing delays, and we have the 2 there because we had 2 propagation and 2 processing delays, and then if we multiply, so the propagation delay and processing delay is seconds. If we multiply this by our throughput, R, which is in terms of bits per second, this product is basically bits. We have the bits as our units. So we have essentially the equivalent number of bits that we wasted, if you like, due to propagation delay and processing delay. Again, divided by the total number of bits in our information frame. So we want to have the amount of time that we waste due to propagation delay and processing delay be as small as possible relative to the information, the length of the information frame. And so all of this is telling us, making the denominator as small as possible, making the numerator as large as possible, all of this is sending us the message that we should have big, long information frames with big, big payloads relative to the overhead bits in the information frame, the processing delay, the propagation delay, and the time spent transmitting our acknowledgements. So let's kind of take a step towards being a little bit more concrete. We've defined all of this in terms of variables, which is great, but now let's plug in some real world numbers to see what kind of efficiencies we actually get in a practical system. And I've got some typical numbers here from 802, the Wi-Fi standard 802.11b. 802.11b is obviously an older standard, but it is one where stop and wait ARQ is used. And we have a bunch of values for each of the variables taken out of the standard. And so the number of data bits in our payload is equal to 80,000, which is half the maximum payload. You can have a variable size frame in Wi-Fi, so I took half the maximum. Our number of overhead bits is 208. The length of our acknowledgement is 112 bits. 2 megabits per second, which is, again, 802.11b, so it's a little bit slower. That means the time we spent transmitting a frame is 40.1 milliseconds. An acknowledgement is only 56 microseconds. That's good, right? Because we want the acknowledgement to be short relative to the information frame. The propagation time I'm going to take as 1 microsecond, which is the maximum allowed by the standard. And the processing time I'm going to assume is 64 microseconds, which again is the maximum allowed by the standard. And so if we take all these numbers, we plug them into our equation, we see that we are 99.3% efficient. So we're very, very close to 1. 99.3, maximum, of course, is 100%. And this is a really great number. If we have a protocol that is, 99% or higher in terms of efficiency, that's a very, very good result. And of course, this is thanks to the fact that we have a very long data frame with a whole bunch of user bits, and everything else, the overhead and the propagation time and stuff like that, is fairly small. However, we have to be a little bit careful because The payload of user data in our information frame is variable. And if we drop that payload down to the minimum, which is 8 bits, so we can have an 802.11b frame that has a user payload as small as 1 byte. When we do that, the efficiency drops to 1.4%, because now all of a sudden all the overhead and propagation time is really, really significant compared to the very small amount of user data that we are sending with each exchange. And this highlights an important point, I think, that I want to make about having engineering knowledge of how networks work. So many of you, if you go into a career in computer networks, won't actually be building network equipment. So the companies out there like Cisco and Nokia, they are the ones that build the network equipment, they define the standards, they write the protocol code, they build the boxes. And so they're the ones that are making all these design decisions. But the companies out there that provide network services, like TELUS, Shaw, Verizon, those companies basically buy network equipment from companies like Cisco and then just deploy them. And lots of engineers work for service provider companies. And even though those engineers are not building the boxes, they are configuring how those networks operate. And there are so many parameters when you're configuring a network that you can choose to sort of optimize your network performance. One of those parameters, let's say you're provisioning an industrial Wi-Fi network, one of those parameters is how big you want your payload to be. And so it's important for the engineers that are provisioning and deploying the networks to have an understanding of how protocols work, because if you didn't realize how important it is for network efficiency to have a large payload relative to the other sort of overhead in your stop and wait ARQ protocol, you could just without knowing better, set your payload to 8 bits and have a very, very low user experience and effective throughput. So anyway, that's just a little bit of a plug for the value of having under the hood knowledge, even if you're not actually writing protocol code. The other thing I would like to say is that the conclusion that we're getting from this discussion so far is obviously make your information bits as big as possible. Just have enormous payloads and drive that efficiency up as high as you possibly can. And that's true so far, except there is one important thing we have not yet taken into account, and that is the probability that some of these frames might be received in error. And so what we're going to do is we're now going to extend this discussion to account for the probability of bit error and frame error in our effective throughput. And we're going to see that there's actually, the picture is maybe not quite as simple as it looks at this point. So if we want to include the effective errors in our stop and wait ARQ efficiency expression, the first thing is to come up with an expression for the probability of frame error. And I'm going to denote probability of frame error as P subscript, P subscript F for frame error. And this is equal to the probability the frame is bad, obviously. And we define that as having one or more bits in error. So the probability frame is bad is equal to 1 minus the probability the frame is good. This is equal to, and in order for the frame to be good, all the bits have to be correct. So this is equal to 1 minus the probability all bits are okay, which is equal to 1 minus the probability Bit 0 is okay, and bit 1 is okay, and all the way up to bit nf minus 1 okay. Because all of these bit errors are independent, this is just the product of all of the bits being okay, and because the probability of error is the same for every single bit, this final expression ends up being equal to 1 minus the probability of a bit error, and I'm going to denote that as PB, raised to the exponent of NF. Right? So the probability that each bit is okay is equal to 1 minus the probability the bit is in error. We have NF of these terms, we multiply them all together, and so that's why we raise it to the exponent of NF. Now, interestingly, if we plot, so what I want to do is I want to take this expression for the probability of frame error, and I want to plot it versus the number of bits in our frame for a particular value of bit error. And that's what I've got on the next slide here. Now, in this slide, to generate this slide, the probability of bit error was equal to 1 times 10 to the minus 5. So that's kind of as low as we can sort of expect in a wireless channel, even with the use of error correction codes. And I really want to just point out how quickly the probability of frame error climbs versus the number of bits in our frame. So on our axis here, this is thousands of bits. So this is 20,000, this is 180,000. The probability of frame error starts at 0 and goes up to 0.9. And in our efficiency example, we took 80,000 bits in our information frame as the value that we use to get our 99.3% efficiency. And so if we select 80,000 bits in this plot, and we sort of go up in a vertical line, and then we go across in a horizontal line, we can see that our probability of frame error is almost 50%. So this now gives us a clue regarding the possible penalty of having long frames. On one hand, having long frames will make the amount of overhead bits we're sending and the amount of time we spend sending our acknowledgement seem relatively small relative to our nice big payloads. However, the longer our frames get, the higher the probability of frame error. And that's because in order for the frame to be good, every single one of those bits has to be received error-free. And the longer we make our frames, the more times we basically roll the dice on transmitting each one of those bits with our probability of bit error, and the more likely it becomes for one or more of those bits to be bad. And so it seems like we've now got a little bit of a trade-off. On one hand, long frames are good because it kind of reduces the impact of the overhead that we add because of our protocol. But on the other hand, long frames are bad because it increases our probability of frame error. And every time we receive a frame in error, we have to waste time retransmitting that frame. So this is kind of an interesting engineering situation. And I think the most interesting situations in engineering are where we have two competing trade-offs. On one hand, in some ways, long frames are good. In other ways, long frames are bad. And it suggests kind of an optimal point where we hit the right kind of trade-off between these two competing interests, if you like, or these two competing effects. And that's really where engineers really add value, right? When the answer isn't immediately obvious, when there's kind of an optimal point to be found, that's where I think we can do the best work. So in order for us to determine an expression for the effective throughput or in order for us to determine an expression for effective stop and wait ARQ throughput that takes errors into account, we need to incorporate some probability theory. And probability theory is really one of the fundamental areas of mathematics that underpin network design. So much of what we do in terms of how we design protocols and how we evaluate the performance is rooted in probability theory, because so much of what happens in a network is random. So the bit errors that occur at the physical layer are random, right? So that's what we're talking about now. But as we're going to find out later on, the traffic patterns across a network like the internet are random as well. And so we're going to be coming back to probability concepts and probability theory over and over again. And this is sort of maybe the first point in the lecture series where we really dive into something where we need to make heavy use of probability concepts. If you're taking this class for credit, you know that I've already pointed out some probability videos that I've done for other courses that I've taught that you can access in order to review some of these concepts. If you're just watching this outside of my class, if you look on my YouTube channel, you'll find that I've got videos for probability course, and a lot of the concepts that I'm talking about are reviewed in those videos. So you can check them out if you want. So the effective throughput, whoops, go back to black. The definition for effective throughput is still going to be the number of user bits that we send divided by the time it takes to send those bits. However, we're going to add an average to the denominator of this expression. So I'm going to say the average time for whoops. The average time for a successful transmission. And I'm going to represent this quantity as T average. The reason why we have to now make the distinction that we're talking about an average time is because every single time we transmit a frame through a channel with errors, our actual transmit time is going to be different. There are times when the frame gets through first try and we don't have to do any retransmissions at all. There are times when we might have to retransmit once. There are times when we might have to retransmit 4 times. And the actual number of times is going to change randomly from one frame transmission to the next. And so we're going to take the average of that. And this average expression is equal to T, which is the total amount of time for a single information frame and ARQ frame to be sent in the error-free situation. So this T is defined in the same way as it was for the error-free case, plus T times the expected value of X, and X is a discrete random variable that represents the number of retransmissions. Right, and it's a discrete random variable because X could be 0, maybe we don't have to retransmit at all. X could be 1 for one retransmission, 2, and so on. And what we're going to do next is we're going to figure out the value for the average of X, or the expected value of X. And so just following the general theory for discrete random variables, the expected value of X is equal to 0 times the probability that our first frame transmission was okay, plus 1 times the probability that the first transmission was bad, right? So we had to do one retransmission, and the second transmission was okay. So the frame got through the second time, plus 2 times the probability the first transmission was bad, and the second transmission was bad, and the third transmission was okay, and so on. So that means the expected value of, the expected value of x is equal to the sum of I equal to 0 to infinity, because in theory, there's a non-zero probability that we can just, every single one of the transmissions will be bad and we'll be retransmitting forever. So our average is equal to the number of retransmissions I times the probability that the first I minus 1, is equal to I, which is the number of retransmissions, which is equal to the probability that we had I bad frames. So this is the probability of frame error raised to the exponent of I, multiplied by the probability that our last transmission actually went through okay, which is 1 minus the probability of f. So this is the general expression for what we wrote out on the previous slide. And sometimes a sum to infinity can seem intimidating, but often there are sort of handy summation identities that allow us to come up with a nice closed form expression for sums to infinity, particularly if the quantities we're summing get smaller and smaller and smaller. And so we can rewrite this expression as 1 minus pf times the sum of I equal to 0 to infinity, I times pf raised to the exponent of I. And as I gets bigger, this term is going to get smaller and smaller. And so we have a handy identity. I equal to 0 to infinity, I times some quantity p to the I. This sum is equal to p times 1 minus p squared, as long as the magnitude of p is less than 1. So using this identity, the average number of retries is equal to 1 minus pf, which is the term we had out front, times pf over 1 minus pf squared equal to pf over 1 minus pf. So a nice, compact expression that we can substitute back into our throughput equation. Okay, so if we go back to our expression for the average time for a stop and wait ARQ exchange, if you remember, it was t plus t times the expected value of x. We can now put our expression for the expected value of x. And if we sort of do some expansion here, we end up getting this very compact expression, t over 1 minus pf. And then if we return to our expression for the average throughput, or sorry, the effective throughput, and I'm going to denote effective throughput, I'm going to go comma E. So this is to denote that this is the expression that accounts for errors. It's the number of user bits we're able to transmit divided by the average amount of time it takes to do an ARQ exchange. So this is just still the total number of bits in our information frame minus the overhead in that frame. And if we substitute in the expression for t average, this is just t divided by 1 minus pf, which is just equal to 1 minus the probability of frame error times nf over n naught divided by t. However, you'll note that this term is just equal to our original expression for effective throughput where we didn't take errors into account. And so the overall effective throughput, with errors is just equal to 1 minus the probability of frame error times the effective throughput without errors. And this, again, I think is a great example of, a mathematical equation just really elegantly showing us how a system behaves and what a system is sensitive to. So if we look specifically at this value for the probability of frame error, if pf is equal to 0, the effective throughput with errors is just equal to the effective throughput without errors, right? So if we don't have any frame errors, we would expect that. However, as this value of pf increases, if pf increases to the point where it's equal to 1, the effective throughput with errors drops to 0, right? Because 1 minus 1 is 0. And so the expression shows that, it sort of goes between these two extremes of, for very low errors, it's basically the same throughput as we had originally before we took retransmissions into account. And at a very high error rate, we're retransmitting so much that the effective throughput experienced by the user basically drops to 0. And so this final plot is a plot of both of the efficiency equations that we've derived so far in this module. We have the first value of efficiency, which is the error-free efficiency, the one that doesn't account for retransmissions. And that's what is shown by the dotted line. Efficiency is on the y-axis of this plot. It goes from 0 to 1. And on the x-axis is the size of the information frame. And so for our first example, when I should say the parameters used to calculate these curves are the same parameters that we've been using all through this module. So all of those values from the Wi-Fi example we did earlier on, as well as a probability of bit error equal to 10 to the minus 5. And so the x-axis, we have the length of our information frame in terms of thousands of bits. And so we did, before we started to look at the errors, we did an error-free example where we had an 80,000, an information frame that was 80,000 bits long. And if we take a vertical line, this is the point that was, I forget, like 99.3% efficient. And of course, as we look at this dotted line, we can see that basically, as we increase the number of bits in our information frame, our efficiency basically just keeps on getting higher and higher and higher. Of course, it never truly reaches 100%, but it just keeps on going and going, because as we increase the size of our frames, our the impact of the the length of the ARQ frames and the processing time and the propagation delay and all that kind of stuff, that impact just gets smaller and smaller because we're transmitting such huge frames. However, the second plot is a plot of efficiency using, taking into account the probability of frame error. And this is, this error efficiency is really just equal to 1 minus the probability of frame error rate multiplied by the efficiency without errors. And when we look at this dotted line, we can see that sure enough, for very short frames, the efficiency with errors basically tracks the efficiency without errors. And so in this very short, do a little bit better. So in this area where we've got a very small payload, the mechanism that dominates our efficiency is the overhead that we're adding because of the ARQ scheme. So our frames are so short that our probability of frame error is relatively small. Remember, the shorter frames have a much lower probability of frame error. And so for this short frame region, we can make very rapid gains by increasing the length of our frame. Errors haven't started to affect us very much yet. And, the longer frames just make the impact of the overhead that we're adding and the propagation delay and all that kind of stuff a lot less. However, we see an interesting thing sort of in the neighborhood of perhaps 10,000 frames, where all of a sudden we hit a maximum and our efficiency actually starts to go down. So what's happening here is our probability of frame error, this PF term, is starting to get really, really big and significant, and it's really starting to hurt us. At the same time, the efficiency gains that we're getting from increasing our payload are starting to level off, right? So we saw a big jump in efficiency gains when we went from a very small frame to, maybe about, perhaps 2,000 here. But after that, we don't really see a big improvement, and the probability of frame error really starts to hurt us. So as a result, we see actually we have an optimal point where, if we have just the right length of frame, we're getting good efficiency because we've got a fairly decent sized payload, but we're not so long that the probability of frame error is really starting to hurt us too much. And this is that optimal point that we talked about a little bit earlier on in the module. And like I said, this is where I think engineers really add value. So understanding these sort of competing trade-offs, long frames overcoming the waste of overhead, but not too long so we don't suffer from frame errors too much. Like, this is the point where an engineering understanding of trade-offs really, I think, can add value. And again, this is something that would not just be in the creation and the definition of protocols, but configuring existing network devices and provisioning them to deploy them in kind of like a service provider context like TELUS or Verizon.